Go ahead. I heard you say you had a question.
Are you talking to me?
I thought so.
That might have been my sister in the background.
Oh, sorry.
You're good. Sorry.
All right, so I made a dumb move there. I forgot to take log of that side. And if you're curious, how I knew that I made a mistake. My number came out negative, which obviously cannot be. It should be a pretty good indicator that I made a mistake. Now that I have another log there, that'll give me another negative number. And that'll make everything all right. So I get 3.97. I'm just going to say that's 4. So 4 years for this machine to depreciate by half of its value. You might hear a lot of times things called half-life. So that's kind of the half-life of its value. Anybody confused? Looks like we lost about 5 people on our transfer to the next meeting. If any of you have their respective information, please remind them that I switched over. I changed the announcement on Blackboard. All right, so let me do this one, and then we can get into the meat of stuff, which is taking derivatives. So suppose the price of a box of popcorn at a movie theater cost this price in 1960, and it cost $2.60 in 2005. Assuming the cost of a box of popcorn increased continuously at a constant rate, determine this rate. So it tells us we're assuming P is the price, and it's some kind of exponential function. And we did that last time, right? We had the PERT formula, P times e to the RT. We have to solve for P0 and R. Notice it says T0 is representing 1960. So we need this equation. We need P of 0, and we need P of 45. So if I plug in 0, then we get E to the R times 0, and this has to equal the original price at that time, which was 0.35. And for 45, we get P0 e to the R times 45, and this has to equal the price for that time, which was $2.60. This first equation, the e to the R times 0, well, e to the 0 we've discussed is 1. So this equation tells us P0 is just 0.35. So then we can come down here and plug that in. And we got to solve for r, so I'm going to divide both sides by 0.35. That's going to result in this equation. So let's see what that comes out as. I think it was nice. Oh, maybe not. Let's just leave it as 2.6 over 0.35 for now. Then if we want to get rid of the e, we have to take the natural log of both sides. So again, these are inverse functions. They cancel. We get 45r. Go to this. Finally solving for r. Sorry about the email noise. Wouldn't be able to hear you guys if I turned off all the sound. I can figure out how to turn that off. All right. So what is that going to give us? So natural log 2.6 divided by 0.35 divided by 45. Something like that. Again, I don't like that, so let me check. There's my 354. Sure, I did something silly again. Yeah, I did quite a bit.
Why did you make 45 into a fraction instead of dividing everything by 45?
It's the same thing. Can you see my screen still?
No. Have you done anything new?
I didn't know if it was showing you what I'm currently looking at or the same looking at the last time I saw the problem, and I got.
It's still showing when you got that 0.04456.
So yeah, I just wrote it that way. If you'd prefer, you may write it like this. Same thing. So this is R, or the rate, which is expected to be a fraction or a small irrational number. So we could find the price for any time t now, because we found P0, which was 0.35, and we found that rate, which is, let's go, what did it say? Tell us the decimal places. No, it didn't tell us this time. So we'll just go to the many I have there. So this is the equation we would use to find the price at any time t. Any questions about that problem? All right, so I got one more here, and I want to at least start the derivatives. So hopefully you guys can help me out with this one. Total cost in dollars for printing X thousand copies of a book is given by this equation. So X is going to be, for instance, it says the cost of printing 12 1,000 copies. So if X is the thousands of copies, X for this would really be 12. Is that clear to everybody?
Yep.
Okay. So the cost, just plug it in. So C of 12. So this is really just 7 in there. So the cost is 86,836, and we'll say 41 cents. All right, if the total cost of printing is 100,000, how many books were printed? Okay, so we set that 100,000 equal to the cost function. So this time, I'm trying to solve for X. So subtract 9,000. Then divide it by the 40,000. So then we have natural log is equal to, it is 2.275. We got to get rid of log, so take e on both sides. Those cancel. Solve for X. We get about 17.456 if I round. And I stopped there because I want thousands of copies. So if I write this as the actual number of copies, that's 17,456. So many copies would need to be printed in order to cost $100,000. So any questions about those? All right.
Hello?
Yeah.
Oh, you can hear me now? Oh my God, thank
You sound really excited about that.
you. Well, I haven't been able to get my mic working for like the past like 2 meetings. So.
Gotcha. All right, so let me just pull up. These are my notes that are already solved. That's not going to do us any good. The next section. All right, so that stuff might have been a little boring for you, and I apologize. So I hope that this is a little more intriguing, because we are studying calculus after all. All right, everybody see section 5.3?
Yep.
All right, thank you. So we've got the properties here, right? They're listed here, 1, 2, and 3. These are the most important when differentiating. So let's talk about the derivative of the natural log. Well, the derivative of natural log is 1 over x. So again, derivative of the natural log is 1 over x. If we start stuffing stuff inside the natural log that is not just x, well, then we get 1 over the inside. I'll give you an example. If I just do, say, log of 2x, well, I still get 1 over the inside, which is 2x. But because there's something other than x in there, I need to use the chain rule. So the derivative of 2x is 2. So in this particular case, we just get 1 over x again. So in general, right, it shows you here on the next step, the derivative for a log that has something else besides just x plugged in is 1 over whatever that inner function is, right, times the derivative of the inner function. So let me go ahead and demonstrate a few of these. So find the derivative of the following functions. Now these first two are just, let's get used to natural log. So this is a very simple derivative, right? The derivative of x cubed is 3x squared. We all know that. Plus derivative of natural log, which is 1 over x. That one's done. The next one then makes it a product, right? These two things are multiplied. So y prime equals, again, derivative of x cubed is 3x squared. But now I'm going to leave the natural log alone. And then add to that, now leave the x cubed alone, and the derivative of natural log is 1 over x. We can slightly simplify this by making this x squared, right? One of these would cancel with one of those. And then both terms have an x squared in them, so you could even factor that out and write it this way. Either of those are acceptable. Okay, now this one is the extension of the derivative of the natural log. So I've got something other than just x in here. So when I take the derivative, my writing keeps disappearing. Is it doing it on your guys' screen as well?
Yeah.
I don't know what's going on. Give me a sec. Man, what is it doing? So my computer's not going to crap out here. It is getting quite warm to the touch. just try one thing. Let's put it on tablet mode, see if that helps. Okay, so y prime, nope, disappeared again. Fantastic. All right. So we're trying to reopen the file. See if it fixes the problem. Nope, disappeared again. Well, isn't this just lovely? Man, what is going on? Let me try this here. Cursor there. And then drawing canvas. There we go. Okay. Tell ya, technology just makes this job even harder. You guys are probably just sitting there going, man, this guy's crazy. Okay, can you see that Y prime?
Yeah, I can see it.
All right.
Yep.
Thank goodness. Whew. All right. So derivative of this function is going to be 1. Come on. You got to be kidding me. 1 over the inside, which is x minus 4, times the derivative of the inside, which in this case is just 1. So y prime is just 1 over x minus 4. All right. So let's look at D here. Maybe my pen's dying. But considering we only have 10 minutes left, I don't want to have to start him over. All right, let's see if I can do it this way. So we've got D here. Nope, I'm on the right. It just keeps doing whatever it wants to. Let's try this again. All right, F prime. Derivative of this natural log, again, we would get 1 over the inside. But we'd also need to multiply by the derivative of the inside. Recall that this is to the 1/2 power. So when I differentiate, that 1/2 comes down in front. I get x squared plus 5. And I have to subtract 1 from the power. So this is really 1 over 2. And we've got square root times square root in the denominator, which means the square root just disappears. Anybody think of another way to do that problem? what if I rewrote it this way? So if I write it like that, rules of logarithms say I can do this. And I guess I missed my 2x in there. So I really need a 2x up there. They're gone. So if I rewrote it this way over here, what's the derivative of this function? Well, 1/2 stays. Derivative of natural log is 1 over the inside times the derivative of the inside. Would you look at that? So just knowing some rules of logarithms and how you might be able to manipulate functions, you can make the problem so much easier on yourself. All right, let's go ahead and do this one. Now this one, I've got a product inside of the log. We know that the log of something times something can be written as the log of the first plus log of the second. So before we take the derivative, let's do that. And this is really foreshadowing what we're going to do with logs. We're going to do something called the logarithmic differentiation, which is introduce a log into a problem that doesn't already have one to make the derivative much easier to take. So if I differentiate both of these now, the derivative of the first gives me 1 over the inside, just like it always does for natural log, times the derivative of the inside, plus the second one gives me derivative, which is 1 over the inside, times derivative of the inside. And the nice thing is, when doing these, we can just leave them like this. We don't have to put them together. So f is very similar. The difference is that now it's a division, which means before I take the derivative, I need to rewrite it as the log of the top minus the log of the bottom. So now when I take the derivative, this is 1 over 3x minus 1 times 3 minus 1 over x minus 1 times 1, and simplifying is that. Please, 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 please do not do this. That is not right. All right, G. We can bring the 2 down first. Actually, no, sorry. This one is the reason for this problem is to show that you can't do that. So I wanted to prove there is a difference between that and that. Those two functions are not equal. Right, this first one, the x is squared. The second, the whole quantity is squared. In this case, you can take the 2 down. In this case, you cannot. So what you might want to do is rewrite it this way if you don't like your chain rule. And so the derivative then, well, we take derivative of log, that's 1 over x, leave the other function alone, plus, leave log alone, take derivative of the second function. Well, that's just 2 over x, natural log x. Which you would also get if you did chain rule. Right, you would bring the 2 down in front, take the derivative of the inside, which is 1 over x, and then you would still have a log x there. So I know I'm doing a lot of stuff. You guys have been pretty quiet. So are there any questions so far? Right, I'm going to assume then that you guys are doing okay and you're just bored. So let me go ahead and introduce yet another topic. Take the logarithm of both sides of the equation and apply logarithmic properties. So these are the steps for logarithmic differentiation. So as I said, looking at this equation right here, it doesn't look very fun to differentiate. Right, there's a product of 2 functions. There is chain rule for both of them, and it just doesn't look fun. Well, if I start the problem by taking the natural log of both sides, then I can separate these two. And then I can even take that 3 down in front of that second log. And this is really the power of using logs for differentiation. So I've got log y on one side, and I've got log of 2 other things on the right. Now notice it says up here, differentiate y with respect to x. Well, we did implicit differentiation, which means when I take the derivative of the natural log of y, I get y prime over y. Now the reason for that is the derivative of natural log is 1 over, so I get 1 over y, and then I have to attach a dy dx or a y prime to it. And then the right-hand side's really nice. I'm going to differentiate each log. The first one would give me 1 over x minus 5, right? 1 over the inside. And the derivative of the inside is just 1. So I'm not going to write it. We don't need it. This second one, there's a 3 in front. We get a 1 over the inside. And the derivative of the inside is 2x. So to simplify that, now the last step is, of course, we want y prime. So we're going to take this y and multiply it on the other side. So y prime is equal to y times everything over here. And so then we would plug in y, which was the entire original equation. It might look ugly, but that was much easier to solve than if we had to do the product and chain rules for everything and then try to put them together. So I think I'm going to leave it there. So someone please remind me that we are on B next time. We'll finish up 5.3 and do 5.4. Any questions about any of the problems that I did today?
Nope.
All right, so I'm going to stop recording.